situation?
It's any number of things. I wish I knew what caused it in the chert. I don't. I know it's the way that we've been drilling wells. We're seeing huge skin damage numbers. Yeah, I think it's a combination of the drilling fluid interacting with the clays, possibly. John, you got any comments on that?
Mississippi chert, no.
Yeah.
But I think predominantly it's related to our building.
No, and that's actually a big difference, and that's why on a build-up curve, even though you can have a heavily skin damaged formation, but the curve will still go up and over very quickly. It's just right there. They call it skin because it's damage that's right there at the wellbore. It doesn't go beyond that.
And it's damage during the drilling process?
Yeah, it's damage during the drilling process, typically.
Well, you can conceivably have skins from a number of other things too. You can have scale, paraffin, asphaltenes, and the skin wouldn't have to be up close to the wellbore. It could be progressively deeper and deeper depending on its nature. Nonetheless.
That is correct, and yeah, I was talking about drilling skin damage, but certainly during the production process, you can have all kinds of things that issue into it. Especially if you do a lot of reservoir simulation, you can actually see the skin number changing over the life of the well. So yeah, there's any number of things, fine, especially during the production process, that can cause it. All those things. Okay. This is just an example of, real quickly, buildups. And the only reason I'm showing this is here we have a very short initial flow period, hardly even shows very little drop. And then we have a longer one, probably a 30-minute, maybe even longer than that. Maybe it looks like an hour flow on the thing. When we shut it in the permeability, this is a 100 millidarcy reservoir. So this is a typical DST, short shut-in, about an hour flow, and then with a 2-hour shut-in, we're here at about 1184 psi. Our initial pressure I've defined here as 1200. That's what this number is up here. So you can see that even on a 100 millidarcy test, after a 2-hour shut-in, we're still not built up to initial reservoir pressure of 1200. We're still about 16 psi short. So we just run it out here to, about a 10-hour shut-in, 12-hour shut-in. We're only about 4 psi short. We run another 10 or 20 hours out here, and we've only picked up 1 psi. So even on a very high permeability reservoir, there again, we've got 100 millidarcies up here, we don't get complete buildup. This just shows you that we still need to extrapolate. You can't take the numbers right off the scout cards and assume that there's any validity to them as far as a good build-up bottom hole pressure. Okay, this is the dissection of a derivative curve. You guys keep hearing about these derivative curves. I think we're going to back up here a little bit and talk a little bit more about them. The derivative is just a way to put the data into a fashion that we can use it. There's a whole bunch of math involved in it that I don't think we need to go into, but it just basically takes the data and puts it in a format that we can get permeability, skin, bottom hole pressure, boundaries, that sort of thing. And there's really 4 primary periods involved in a well test. Whoa, didn't mean to do that. And we're going to go from early time, which is over here, to late time, which is over here during the shut-in period. And we're analyzing the shut-in period here. This early time period here, where I've drawn this red line, is what we call a unit slope. It's a slope of 1. This is the wellbore storage period. So I'm saying it goes from this arrow here backwards. And that's the period where all we're actually seeing is the wellbore itself. If there's any doctoral candidates here, we can argue about that definition a little bit earlier, but for our purpose, from a practical aspect, all we're looking at is the wellbore in this period. This period from this arrow to this arrow is a transient period. And it's a period that you're kind of making a shift from the wellbore data, which doesn't really tell you anything about the formation, into the radial flow period that does tell you about the formation. So it's important that you be able to recognize where it is, but you don't really analyze that. All right, this is where the rubber meets the road, is this period here. In this case, this is a radial flow where this derivative curve is flat. And you can see this little line that I've drawn in here, whatever color that would be, turquoise. I've drawn that line through there so you can see it. As we talked before in the ATMS program that Paul gives you, this is the only type of analysis that you can do, is putting this flat line through here. So in this case, when I can just superimpose this line on the flat portion of the curve, that tells me that I've got roughly 98 millidarcies of perm, a negative 0.1 skin, and a P star of 1200 psi. After this point, you'll see that the derivative curve drops off dramatically. Now, most tests that you're going to look at are not going to be shut in long enough to see this portion of the curve. This can take anything from hours to weeks to achieve. And it's called the depletion or steady state period. And that is where you've actually, the pressure wave has hit the boundaries of all the boundaries in the reservoir, and the reservoir is depleting at a constant rate throughout the reservoir. So if you do see this big downward tick like that, that means that the test probably did see the boundaries of the reservoir. Okay, where we were was, I classify well tests into three different types of tests. The one of immediate interest is the DST. It's what's known as a transient test. And a transient test is a test where you don't actually reach the reservoir limits. The pressure wave, if you can imagine throwing a rock out into a lake and you watch the pressure wave go, the transient test is one where you just see the pressure waves going out, but they don't hit the sides of the lake. A steady state test is one where you watch it long enough that the pressure wave hits the side of the lake and then starts bouncing back. There's a couple of key differences in the results that you get from the test. In a transient test, it's used to define the reservoir character, primarily permeability and skin. The other thing it'll typically issue permeability, skin, and reservoir pressure. However, in most cases, it's not going to tell you anything about the size of the reservoir. And that's one of the most common things I get asked is after DST is how big is the reservoir, and typically you're not going to have any idea at all because you're just not investigating that far into the formation. Okay, it's cheap compared to other types of tests. It's probably the best method of determining permeability in skin. It is your best chance to measure your initial reservoir pressure. Almost instant gratification because you pull it out, you take a look at it, and you have your results. And you can do multiple runs if need be. The multiple runs come in handy where you have a case like Paul showed us earlier where the pressure, the shut-in pressures drop after a big drop between the initial shut-in and the final shut-in. Whenever I see that, my standard answer is to go back and run another test. And if the next test shows that lower pressure, then you know you're in trouble. Downside, limited depth of investigation. That's the biggest thing. You're just not testing long enough to see very far.